Hello, and welcome to my session on decomposing the long-time behavior of dynamical systems through linear regression. But before we can talk about decomposing systems, we have to talk about a related problem of predicting them. So let's say that we have this system Lorenz and this observable variable, which is the state space feed, and we want to predict the long-term average. So here I have a little bit of a trajectory in Lorenz, and what's the state space feed on this trajectory. And of course, this is just an example. You can replace Lorenz with your favorite system and replace V with your favorite observable, and everything will still be the same. But at least in the Lorenz case, this is what happens. As you let this trajectory run, you get more and more values. And eventually you have a lot of values. You kind of flesh out the entire attractor here, and you get a really good average value for your observable, which in this case is just under 100. So you get a lot of data, and then this gives you a really high quality prediction. However, this isn't a real prediction, right? Because we just measured it. We just ran the system for a long time and took an average value. So it's not really predicting anything, it's just measuring it. So it's cheating, right? This is like if you ask your friend to describe a coffee cup to you, but then they just ship the coffee cup to you instead of actually describing it. It's just a cheating way to do it, right? So this is, by the way, exactly what Moody diagrams are. Moody, if you didn't know, solved the entire fluid turbulence problem in 1944 by making a bunch of measurements and putting on a chart. So now the engineers can do their pipe flow calculations, right? But again, this is just measuring and shipping it to the engineers in this case, right? So it's the same variety of, for our purposes, we're going to call this cheating. So let's go back to the problem again. How do you predict the long-term average without just measuring it? It's under stipulation. Don't cheat. You have to actually predict it somehow. So the idea of this talk is going to be that you should use short impressions instead of using a big long trajectory. So what is a short impression? It's, oh my gosh, look, it's 19th century impressionist artist Claude Monet here to explain impressions to us. It's little bursts of information about the system. So instead of using a long trajectory, which we consider cheating, we use small little bursts. So for example, for the coffee cup, you might use this burst and that burst and that burst, and you need to combine them somehow. So you give some instructions on how to combine this. And this is a different description of the coffee mug, which is hopefully more compressed because it's short impressions of long trajectories. All right, but this is kind of begging the question, which impression should we use if we should use impressions? And for us, we're going to use periodic orbits of the system. So here's a periodic orbit of Lorenz. What's a periodic orbit? It's just a trajectory which, after some amount of time, it closes back on itself. You get back to where you started. And all right, so this particular one doesn't matter, but why would you use orbits? The reason for that is that if you use more and more orbits, so here I'm adding more and more orbits, it kind of fills out the attractor in a very similar way to just running a long trajectory. More orbits, more filling out of the attractor, right? And that said, we're going to use orbits because they're very convenient for us. But if orbits are not convenient for you, what may be convenient is just using little scraps of simulation data. So any little trajectories that you use, as long as you're making sure that you have this property where you fill out the attractor, right? You want to make sure that happens. Provided that happens, you can use whatever kind of trajectory scrap you want. Cool. So we want to make predictions about observables though. So let's measure the observables using the orbits by just, you let your trajectory run and you plot the observable over the orbit. That's what I've plotted here. And you take the average. So that's this purple line. And I've just written that down over here. So if we do this with more orbits and you add more orbits, eventually you get a whole bunch of orbits, you get a whole bunch of their averages, and you start filling out this kind of number line of your different orbit observable averages over the orbit. And actually that's the only important information here. So get rid of the rest of this. We kind of have the spectrum of the possible observable values over the different orbits. So you can think of this as like a spectrum from quantum mechanics, right? Because it's the observable value on the states. So that's just an analogy, right? But it's a pretty good one because we're decomposing the system. Now, of course, we don't want the orbit averages, we want the actual average. So what we're going to do is combine them as using weights. So this is just going to be a linear combination. So I've drawn this kind of like a neural network, right? This kind of diagrammatic format, but I promise this is just doing a linear combination. Here's the formula. So the actual average that you want of the long-term average, right? That should be a weighted sum of the orbit averages with some weights that are yet to be determined. All right, so let's think a little bit here. So the traditional way to do this is to think of your orbits as kind of decomposing the state space. So you have like one orbit here, another orbit there, and as your trajectory runs, it wanders probabilistically, like a Markov model, between the different orbits. Okay, so it's on this one for a little while, and it instantly takes somewhere else, somewhere else, somewhere else. And there's some invariant distribution that you get to with the Markov distribution. And under that scheme, you get the weights as the probability that you're on any given orbit, which probabilities should be non-negative and they should be normalized. So it should sum to 1. Right? Okay. And also there's this exact theory called periodic orbit theory, where if you know all the orbits, so here we only know 4 orbits, but there's actually infinitely many orbits. If you know infinitely many orbits, you can compute their exact weights using this theory, and those weights will be non-negative and normalized. And this is a variant of periodic orbit theory where you can do finitely many orbits, and that one is also non-negative and normalized. So basically, 100% of our predictions here say that these weights, they should definitely be non-negative and normalized. That's these two conditions, non-negative, normalized. And if they are, then for sure this actual average expectation value V, that should lie in this gray region, which is between the lowest and the highest orbit average. Because of this non-negativity normalized, it has to be in between. So let's see what it actually is. And oh no, of course it's not. It's way outside. So what happened here? Well, this is actually an experimental result, which is that the weights should be negative somehow here. And here, homework problem, figure out which observable you have to choose in order to prove that the weights should be normalized, because they definitely should be normalized. This result is telling us that it should be negative weights. So this condition is violated and this one is kept. And this is only true for a finite number of orbits, because if you add more and more orbit averages, eventually this gray region expands and there's no problem anymore because the actual average gets inside of the gray region. So the result is that for a finite number of orbits, sometimes you need to use negative weights. All right, so knowing this though, all of our theories are going to give us positive weights. So how we're going to deal with this, we need a new way to come up with weights. So let's look at how we do that. And the idea is to go back to this equation that we had before, which is just actual average is the weighted sum of orbit averages. And this should hold for any observable, right? So you can put some observable psi in there. And each observable that you put in these brackets gives you a linear equation for the weights. So it's a linear constraint on psi. And of course, we can use any observable. We chose Gaussians. We figured out these work pretty well for this purpose. And how do you come up with a whole bunch of these in order to have a whole bunch of constraints on your system is that you just kind of litter them all over your state space. So anywhere that your trajectory visits, you want to have some Gaussians there to constrain the system near that location to have the appropriate weights. And you can put as many Gaussians as you want, of course, because you have as many points as you want. So eventually you have more Gaussians than weights. So it'll be over constrained. You can solve the linear system. So that's going to be our formula for WP, is that you just take the least squares solution of the system of linear constraints. All right, so all that's left to do is you have to construct this system, right? Because once we construct it, you just like throw this in MATLAB. It's a finite size matrix and you get your weights. So now to construct this, we need to compute the left-hand side and the right-hand side, of course. And the right-hand side is really easy to compute. This is just the orbit averages that we did before. You only have to like go over one cycle of the orbit, and it's like a finite size trajectory, right? So that's something that we can do very well. However, this left-hand side requires a long-term average or long trajectory to compute its value, right? So it seems like we have to cheat here because we have to somehow have this long-term average without knowing the weights in the first place. But I would argue this is not quite cheating, because once you do this, just one time ever, you have the weights for your system. And then every single time after that, you just reuse these weights. You never have to go back to this long trajectory approach. So this is legitimately a speed up here once you have the weights. So not cheating. But okay, that's all well and good. But does this actually work? Hopefully it does, or we'll be talking about it right now. Here's our results graph. Okay, so remember, everything here depends on sigma, which is the width of those Gaussian observables that we use. So all this sigma stuff is our method. And you can see already that the error is a lot better than periodic orbit theory, and it's a lot better than just using random weights. And in fact, the x-axis here is the number of orbits that you use. So it actually gets better when you use more orbits. That's good. And in fact, this error is normalized. So that's the 10 to the 0 line here is the error associated with the data that you put in, which is this red stuff in the box here. So you put in a whole bunch of work up front to get some good weights, and as much work as you put in, that's how well the fact that these red and yellow lines are next to this black line tells you that the weights do as good of a job as just the input data that you used. So that's basically saying, mission accomplished, the weights reconstruction impressionist thing. This is equal to just just having the actual data in the first place. So that's awesome. This is exactly what I want to see. So of course, there's a lot more to the story, so you should go read our paper when it comes out. Here's some teaser graphs for you. So future directions to consider: how do you choose sigma? Because you see the performance depends on sigma, so who knows, right? And are Gaussians the best observable to use in this situation, or even good observable? We also want to try to scale this up. So we did this all for Lorenz, right? But everything here should, in theory, you can compute it for like, Navier-Stokes or whatever, fluid turbulence. So that's a good problem to solve. Cool. And I want to thank my co-authors, especially Joshua. You're the main two authors on this paper. Special thanks to everyone here for helping me be at March meeting this year. And also, please hire me as a grad student if you are on one of these universities. Reach out. Thank you. And if you have any questions, you can email me at this email address. I'm not here live, obviously, so yes, shoot me an email and I'll get back to you.